In this section, I'll tell you 3 ways to prove a language is undecidable. These 3 ways are diagonalization, reduction, and the rest theorem. Using diagonalization to prove a language is undecidable is virtually a proof by contradiction. We first assume the language L to prove is decided by some Turing machine H. Then we construct another machine D that uses H as a subroutine. After that, we analyze possible results of running D on its own encoding D. You might think, how can a machine run on itself? Well, we are not running the machine on itself, but on the encoding of itself. It's like you have written a program that takes an input string. Once your program is written, we can copy the code and treat it as a string and feed it to your program. Okay, back to the analyzation. In step 4, we show that with the definition of D in step 2, we get a contradiction in both possible cases. They are, if the encoding of D is in LD, with some intermediate reasoning, we find out that D actually rejects D, which is the opposite of what it should do. And in the same way, if the encoding of D is not in LD, with some intermediate reasoning, we find out that D actually accepts the encoding of D, which is still the opposite of what it should do. So whether the encoding of D is in LD or is not in LD, D cannot work properly to decide it. So our assumption in the first step must be false, and L should be undecidable. In some cases, you don't even need to construct another machine to achieve a contradiction. You can use H on the encoding of it directly. With the definition of H and some intermediate reasoning, we show that H accepts its encoding when it should reject, and it rejects its encoding when it should accept. Now let's use an example to demonstrate this idea. We have a language K consisting of machine codings M, where M is a Turing machine and M does not accept its own encoding. We want to prove this language is undecidable. According to the procedures, we first assume K is decidable by a Turing machine H. This means K equals LH. And for each string in K, H accepts it. And for each string not in K, H rejects it. In the second step, we analyze possible results on running H on its own encoding. If the encoding of H is in K, then since H decides K, H should accept the encoding of H. Since the encoding of H is in K, by definition of K, H does not accept H. Earlier we said that H should accept H using the knowledge that H is a decider of K. Now we say H does not accept H using the knowledge of the definition of K. If both these 2 pieces of knowledge are true, then we reached a contradiction. Similarly, if the encoding of H is not in K, since H decides K, H should reject the encoding of H. But by the definition of K, H accepts the encoding of H, also a contradiction. So in both possible cases of the membership of the encoding of H in K, we reached a contradiction. So our assumption must be wrong and K must be undecidable. Note that in this proof, you need to show that in both cases a contradiction is achieved. In this proof, we did not construct another machine to reach the contradiction. we used H directly. In some other proofs, you may need to construct another machine to do the job. Now let's see a similar problem. It's actually our homework problem 1. We have the language L consisting of Turing machine encodings where M is in LM, meaning that the machine M accepts its own encoding. This is the opposite case of the example I just showed. So you might think you can just copy and paste that proof structure here. It turns out that it does not work here. If we assume L is decidable by H, then L equals LH. In the reasoning, if the encoding of H is in L, since H is a decider of L, H should accept H. By definition of L, the encoding of H is in LH, which is equal to L. So H is doing the right thing. There is no contradiction. And we have similar results if the encoding of H is not in L. But we ask you to prove L is undecidable. You must be able to achieve some contradiction somewhere, right? So what's the problem? Well, H on its own encoding resulting in no contradiction does not mean some other machine performs the same. Probably you need to construct another machine and run that machine on its encoding. That means you should construct another machine D and analyze this machine D on its own encoding. This D should use H as a subroutine. The way you construct D should satisfy that if the encoding of D is in LD, then using some intermediate reasoning, you reach the conclusion that the encoding of D is not in LD. And similarly, in the other case, you start with the encoding of D not in LD, but reach a conclusion that the encoding of D is in LD. So how you construct D is the key. If you have no idea how to do that, I recommend you check the trick used in the textbook, page 207. Now let's move on to the second method to prove a language is undecidable. It's reduction, and it is the most widely used method. The mechanism of it is still a proof by contradiction. Say we want to prove a language B is undecidable. First, we assume B is decidable by a Turing machine H. Then we select an undecidable language A. Yes, we here intentionally select an undecidable one. The purpose is that we want to reach a contradiction. Here A is undecidable, we know that. Later, we show that with the assumption in step 1, A is decidable by some machine. Thus, a contradiction is formed. That's what step 3 does. We creatively construct a Turing machine D that decides A using H as a subroutine. Step 2 and 3 need some cleverness. B should be related to A in some obvious way for your convenience in the proof. This whole process can be written as A less than or equal to B. We read it as A reduced to B. The meaning of it is, if B is decidable, then A is also decidable. If A is not decidable, then B is also not decidable. Let me use an example to show you how exactly this works. We want to prove the language EQNT is undecidable. We want to check whether an NFA and a Turing machine define the same language. In the proof, we first assume EQNT is decidable by a Turing machine H. In the next step, we should select a known undecidable language, and we pick hot TM. In hot TM, it checks whether a Turing machine halts on its input. This language is proved to be undecidable in the textbook, page 217. In the third step, we try to construct a Turing machine D that decides hot TM. This step needs some thinking. We need to figure out how we construct N and T so that running H on NT tells us whether M halts on W or not. More specifically, we want to construct N and T for use such that these two statements are true. If Ln equals Lt, then M halts on W. And if Ln does not equal to Lt, then M does not halt on W. This is still kind of too general for us to construct N and T, so we further narrow down the options for N and T. We restrict Ln and Lt to be the set of all strings over sigma. With this clear definition, it is very easy to construct N. We only need one state and add a self loop on every symbol in sigma. And mark this state as both start state and accept state. Constructing T, however, needs some tricks. We want Lt to be sigma star if and only if M halts on W. With this restriction, we can make use of halt TM later on. So we define T as on its input string X. T does not care what its own input is. It simulates M on W instead. If M halts on W, then T accepts X. If M loops on W, then of course T also loops because the first step can't be finished. And if M rejects W, then T rejects W. With these two machines at hand, we can finally construct D that decides hot TM. D equals, on its input MW, it first constructs N and T as described before. Then it runs H on NT. If H accepts NT, then D accepts MW. If H rejects NT, then D rejects MW. Note that this H is a decider, so it always halts on its input, which makes D always halts, since it either ends in the if branch or the else branch. Now we show that this constructed D actually decides hot TM. We analyze two cases, when a string is in hot TM and when a string is not in hot TM. So if MW is in hot TM, then by definition of hot TM, M halts on W, which implies Lt equals Ln and they both equal sigma star. Thus, H accepts NT and D accepts MW. In the other case, if MW is not in hot TM, then by definition of hot TM, M does not halt on W, which implies Lt is not equal to Ln. Thus, H rejects NT and D rejects MW. So in both cases, D correctly accepts and rejects strings. And D is a decider. So D decides hot TM. But we know that hot TM is undecidable. What goes wrong? It must be the assumption we made at the very beginning that EQNT is decidable. So we can conclude now that our assumption is wrong and EQNT is actually not decidable. Now let's move on to the third way to prove a language is undecidable. It's Rice's theorem. The theorem is very simple. It says any non-trivial property of the language of a Turing machine is undecidable. You might think, with this theorem, you probably don't need to do any work, but declare that the language you want to prove is a non-trivial property. Well, it's simple to use, but not so simple. You still need to do a little bit of work. So let's analyze this theorem more carefully before jumping to use it. First, if a property is trivial, then either every language has this property or no languages have this property. Second, P is a property of languages of a Turing machine if P is a subset of T, where T is the set of all possible Turing machine encodings. And if LM1 equals LM2, then either both M1 and M2 are in this property P or both are not in this property P. We say P is a property, but if you take a look at it carefully, you will find it's a language. It contains all Turing machines that satisfy some properties or requirements. Third, P is a non-trivial property if we can find a machine M1 that is in P and find another machine M2 that is not in P. In this third step, we need to find those specific machines. Great! We now have a good understanding of this Rice theorem. Next, we'll discuss when and how to use it. When to use? When the language L you want to prove has the form, the encodings of M with some property about LM. And your goal is to prove this language L is undecidable. How to use? You first show that this language is a subset of T. This step is easy. You only need to show that member strings of L are Turing machine encodings. Then you show that if some general Turing machine M1 and M2 define the same language, then either both of them are in L or both of them are not in L. Finally, you provide two specific Turing machines, M1 and M2, such that M1 is in L and M2 is not in L. Usually, these two machines are simple. I bet you're confused how we actually show these three steps. Let's dive into an example. We want to prove H epsilon is undecidable. H epsilon contains all Turing machine encodings, and these Turing machines accept epsilon. First, we check whether we can use Rice's theorem. Well, H epsilon is of the correct form. Member strings are Turing machine encodings. And it talks about some property of this language defined by this input machine. And our goal is to prove it's undecidable. So we are good to use Rice's theorem. Now we show how we use the Rice's theorem to prove this language is undecidable. We first show that H epsilon is a subset of T. To do so, we only need to show that every string in H epsilon is also in T. The reasoning goes like this. If W is in H epsilon, then W equals M enclosed by angle brackets. That means it's an encoding of some machine M. And M is a Turing machine. So by definition of T, W is in T. Okay, first requirement, check. Next, we show H epsilon is a property of languages. Given two machines, M1 and M2, If LM1 equals LM2, then we analyze two cases. The first case is M1 is in H epsilon. This means M1 accepts epsilon, so epsilon is in LM1. Since LM1 equals LM2, epsilon is also in LM2, and M2 accepts epsilon. This implies M2 is also in H epsilon. In the second case, M1 is not in H epsilon. This means M1 does not accept epsilon, either by rejecting it or by looping on it. So epsilon is not in LM1. Since LM1 equals LM2, epsilon is not in LM2 either. Thus, M2 does not accept epsilon, and M2 is not in H epsilon as a result. Good. The second requirement, check. Finally, we give two Turing machines and show that one is in H epsilon and one is not. We define a specific Turing machine M1 that accepts every input string. It is easy to construct such a machine. We only need to assign the accept state as the starting state. M1 is in H epsilon because M1 accepts epsilon. We then define another specific Turing machine M2 that rejects every input string. We construct it by assigning the reject state to the starting state. M2 is not in H epsilon because M2 does not accept epsilon. As I said before, these two machines are simple, and these two machines either accept everything or reject everything are widely used in such proofs when using Rice theorem. Now we can conclude that H epsilon is a non-trivial property of languages of Turing machines. Thus, it's undecidable. Great! We have talked about the three methods. Let's use them to solve some homework problems. There are 6 languages in problem 2 for you to think about. For each language, you need to judge whether it is decidable or not. If it is decidable, then you construct a Turing machine that decides it. If it is not, then you use reduction or Rice theorem to prove it's not decidable. You can use any undecidable languages in the textbook to form a contradiction if you use reduction. I personally think Rice theorem is easier in some cases. Okay, let's analyze those languages. If you look at L2, it's so similar to the example I talked before. So can you make use of that proof by modifying a little bit? L3 is tricky. Think about, do you need to check infinite many W's or only a bounded number of W's? Remember that reading all symbols in an input string of n symbols takes at least n steps, because you need to check each symbol in each step. For L4, check the textbook page 219 for a similar question. In that example, LM is a regular language. Here, it's a context-free language. How can you modify that proof? For L5, can you use Rice theorem or can you not? If you think you can, do you need to transfer L5 to some another language for consideration? If you think you cannot use Rice theorem, then try reduction. Can you fix the machine among M1 and M2 and the value of k to get a special case for reduction? Can you make use of ETM in page 217 in the textbook? Alright, that's all for this recitation. If you have any questions, leave a comment below.